Yeah. Can you see my screen?
Perfectly.
Okay, perfect. So yeah, hi, I'm Isabel, and I am currently doing my last year of PhD at the University of Oslo, and I'm going to present what I've been working on for the past 3 years of my project. And it's we've been focusing on a sample of local ultraluminous infrared galaxies, focusing on the molecular gas using tracers CO and atomic carbon, using observations from APEX and ALMA ACA. So why ULIRGs? These sources are actually mostly in the local universe. They're mostly galaxy mergers. So that means that they are great sources for studying feedback processes, because since they are merging, they are very chaotic, they are dusty and gas rich, and they can be powered by star formation rate, the accelerated star formation rate, and AGN activity. So in turn, these feedback processes can affect the gases in all phases, but right now we want to focus on the molecular gas phase, which can be very affected by the gravity in these merging processes. This gas is found not only in the rotating disk, but it can also be found in outflows, inflows, and tidal tails. But however, there are still many mysteries that still need to be answered, such as the properties of the physical properties of the gas, such as the mass, the temperature, the density, and the energetics of this molecular gas. The molecular gas, however, as I said, can be also found in very extended and diffuse emissions, such as outflows or tidal tails. But we are still not very sure what are the extents of these components, and how are the excitation conditions in the outflowing and the non-outflowing gas. So also, just as one of the two speakers in the morning session, that she was talking about the cross-correlation in different gas tracers, the alpha CO factor, it's very uncertain because it depends on many things. But if we use different independent gas tracers, maybe we can constrain it a bit more. So this is why in our study, we wanted to tackle a statistically sound sample of 40 local ULIRGs and study not only CO, which is the most common and usually the tracer that you go to when you trace the bulk of the molecular gas, but we also wanted to include the atomic carbon line. And in particular, sorry, we wanted to study or focus on the diffuse unextended emission. So one of the most striking studies was the one performed on the Galaxy NGC 6240 by Ciccone et al. In 2018. And they found where they just studied the CO120, CO221, and the atomic carbon line. And they performed both a spatially resolved analysis and an integrated flux analysis. And what they found is that they actually, from these two separate analyses, they retrieve already different alpha CO factors and different ratios, line ratios, for the outflowing and non-outflowing gas. And this can already be picked up not only by the spatially resolved analysis, but also from the integrated spectra. So this is why we wanted to perform this sort of same analysis in a sample of more galaxies, now 40 ultraluminous infrared galaxies, to understand whether this NGC 6240 is a rule of thumb or is it just an exception in one. So the sample selection, it was we selected our sample from galaxies, ultraluminous infrared galaxies that were already observed and detected in OH by Herschel. And most of them actually show this P Cygni profile, such as the one seen here, which is an ambiguous detection of molecular outflows. We also wanted to maximize the overlap with the APEX and the ACA and ALMA public archives to complement the data that we had in hand. And in the end, what we end up, it's a sample of 40 sources dominated by ULIRGs, but we also have some LIRGs. And as I said, it's in the local universe, so the redshift below 0.2, AGN fractions ranging from 0% up to 90%, and star formation rates ranging from a couple of solar masses a year up to a couple of hundreds, since, as I said, you can have starburst processes in these sources. Our observing strategy, as I said, since we are focusing on the extended and diffuse emission of these sources, then we want to prioritize the high sensitivity to large-scale structures data. So in that way, we prioritize the APEX data, then we went to ACA, and lastly, we use the ALMA data if we didn't have anything else. So in the end, we end up with a large data coverage with many line transitions for many of the sources, and we re-reduced systematically all the data, and in particular for the interferometric data that we know we are losing the zero spacing, so the total flux. We were careful and we did our best, and in the end we extracted the spectra from the apertures that maximize the flux. So in the end, we end up with a compendium such as this one of a lot of data sets for many different transitions and for many different sources, and it was all consistently re-reduced. So our spectral fitting procedure was using simultaneous fit with multiple Gaussians for the CO lines. So we did it simultaneously because in that way we reduced the degeneracies that come with fitting multiple Gaussians to one emission line. So in this way, we can actually, when we do such a simultaneous fit, we can also study any possible dependencies of the line ratios with high velocity gas that can be traced either by high central velocity of the Gaussian or by high velocity dispersion of the component. The C1, though, the atomic carbon line, we fit it separately because overall it had lower signal to noise ratio. And in this way, we kind of actually avoided assuming a priori that C1 and CO share the same kinematics. So yeah, after gathering all the data and reducing and fitting, we actually go on and we estimate an alpha CO factor based on the C1 line. So this is working under the assumption that C1 and CO are tracing the same gas, at least averaged over galactic scales, which has been supported by previous studies where they find almost linear relations between C1 and CO. And actually, C1 can be sensitive to the so-called CO dark gas, which is gas where CO is depleted either by cosmic ray or high radiation fields. We also make the assumption that at least in most extragalactic scenarios, C1 is optically thin as opposed to the very optically thick low JCO lines. And as we heard also from two speakers before me, the main uncertainties for estimating the molecular gas based on C1, it comes from the species abundance and this excitation factor called Q1 to 0. But if we make these sort of assumptions, we kind of go and plug it into our sample, and we retrieve a value of the alpha CO that it's 1.7, that it's higher than the commonly used one for ULIRGs in the literature, which is 0.8 by Downs and Solomon. And it's actually in agreement with recent studies performed on similar sources. But okay, now we can go and study the global CO line ratios. And what we find, it's very remarkable values for our galaxies, because most of them are actually, so if you compare to the normal galaxy population that it's in the shaded gray area in those plots, we see that our distribution of ratios are shifted towards much larger values. And in particular, if you focus, for example, in the ratio R2 to 1, which is most of them are higher than 1, that's really rare in the universe. And those values larger than 1 can actually need to be explained not only by excitation, but also by optical effects, optical depth effects. So in the end, when we study actually the possible correlations between the global CO line ratios and galaxy properties such as infrared luminosity, star formation rate, AGN, luminosity, depletion time, so on and so forth, it is really hard for us actually to retrieve any statistical or any significant trends. And we kind of think it's because we are probing such a narrow dynamic range in galaxy properties, as all of these sources are very extreme, that it's hard to retrieve normal scaling relations that you see in normal disk galaxies. However, for the ratio R2 to 1, we do retrieve some marginal statistical trends with infrared luminosity and with star formation rate. But overall, what this tells us is that these low JCO lines actually are very poor tracers of the heating mechanisms in these galaxies, at least. But as I said, since we fitted simultaneously all the CO transitions that we had for different sources, then we could study any possible trends with between the line ratios and the velocity of the gas. And what we find is that we do not find any visible trend, and we only pick up one for the ratio R2 to 1, and it's only when we take into account the error bars. And this ratio, actually, it's the least sensitive to excitation conditions, right? So even though we see some sources highlighted with the red circle and with ratios R3 to 1 that are a bit higher for high sigma or high B components, this is not the rule of thumb. And since we do not see that for the ratio R3 to 1, but we see it for R2 to 1, then this strengthens this idea that these high ratios that we observe are actually driven by optical depth effects rather than excitation. So in the end, what we are kind of saying is that what we observed for NGC 60 to 40, it's not maybe a rule of thumb, but it's just a very exceptional source. Now we can study the global RC1-CO line ratio. It is very hard to compare to normal disk galaxy population because of the very sparse measurements of C1 in the local universe in normal galaxies. But there is this study by Zhao 2019 where they studied these 15 nearby galaxies, but they range from C4 to H2 liners. It's a very diverse sample. And what they retrieve is a median value of 0.11 compared to our value of 0.18, where we find that our sources still lie very high in this distribution of ratios. Yes, so, but okay, so how is it, like, how accurate is it, this assumption that C1 and C1 are independent and that we can use them independently and they are concomitant? As I said in the past, and also in our study, we find the same result, that the luminosities are actually almost linear, and they suggest in the end that they arise from similar regions in the galaxies, at least average over galactic scales. But since we fitted the lines separately, we also wanted to test, like, okay, do they share the same kinematics? So we tested this by just comparing the line widths of the lines of these two tracers. And what we find, yes, perfect. And what we find, it's a very interesting result where actually on average, the C1 lines appear to be narrower than the C1 lines in our sample. And if we plot NGC 60 to 40 in the fit line that we plotted, that we found, the NGC 60 to 40 actually lies very nicely on top of that fit. So this needs to be, of course, checked with larger statistics, but there may be possible causes for these narrower C1 lines as opposed to the CO lines. Maybe there's depletion of carbon in the line wings, but this would be at odds with the theoretical predictions of the CO dark gas in outflows. Or maybe there's also some optical depth effects causing some little mass in high velocity components, and therefore the C1 line is fainter in these broad line wings. But then again, this needs to be further studied. Now, since we based our sample in sources that had already OH data, we kind of wanted to exploit this data, and we studied the global line ratios with the OH maximal velocity or equivalent widths. And then again, we retrieved no statistically significant trends. So this is still very puzzling because we still don't know very well what is the driver for these high line ratios found in these galaxies. Maybe since there are sources such as R220 where they actually find very high ratios when they focus on the nuclear region of the source, where they are sure that there is a molecular outflow there, but when they study the total galaxy average ratio, it's actually lower. Maybe this is the effect that we are seeing in our sample, that these ratios are kind of washed out in large scales. So yeah, I come to the conclusions. Basically what we did was we used CO and C1 as independent molecular gas tracers to derive alpha CO factors. We probe a very narrow range, dynamical range in galaxy properties, and it's proven to be difficult to retrieve galaxy scaling relations for this ULIRG population. These CO line ratios are actually really high for these sources, but we still don't know what is the driver. And we need higher JCO line data to actually perform a better CO sled analysis. And maybe just by the difference in the kinematics in CO and C1, maybe this could be hinted to different behaviors for the two different gas tracers. And that's it. Thank you.
Thank you very much, Isabel, for this very nice talk. It was a lot of work. Thank you. So are there any questions?
Could I?
Sure.
Very
yeah.
interesting talk. Thank you. It's a curiosity. What is the spatial distribution of this CO line? Because you have large scale information, right, from your observation.
Yeah.
So this could be interesting for your work, or you are only more focused on integrated flux?
So yeah, so right now we wanted to do the integrated flux analysis because of what we saw in GC6040. Right now, because so I haven't checked at all at the spatial distribution of the gas in these galaxies, because as I said, since we were focusing on the diffuse extended emission, we actually prioritized APEX data. So in APEX, we lack the spatial information, right? So right now, I have no idea. Then again, these sources, most of them are mergers. So they are very chaotic when you look at them in the optical. So the gas, it's probably going to be a mix of rotating disks, but also tidal tails going all around. But I haven't properly checked this.
Okay, thank you. Thank you very much.
So Francesco, you can ask your question, please.
Hi, Isabel. Very interesting talk. I was wondering if you have any estimates of the amount of flux that may be missed in the observation that you have, and if this quantity is comparable between the C1 and the CO.
Okay, I'm gonna answer the first thing. So we have an estimate for the C1. Okay, so we estimate that in the end, we don't use that much data from ALMA, only for CO120, and most of them actually we tried them to be for ACA, so that we lose the least possible flux, and we estimate a missing flux of maybe 20 to 30% for the CO120. And for the C1 data, we actually, most of the data that we use, it's from APEX. So we are hopefully not losing any flux there, unless there is some pointing issues or something. But I don't know if that answers your question.
If I may, I have another question related to the alpha CO.
Yeah.
As you know, alpha CO strongly depends on metallicity. And do you have any metallicity information to constrain the alpha CO?
No, we are not using any metallicity information here. So as I said, we only use the C1 line to estimate the molecular gas, and then we plug that into the information, into the equation to estimate the alpha CO. So yes, of course, the alpha CO is going to vary a lot within these sources, and this average value is just going to correspond to the dominant environment in these galaxies. But no, we're not taking into account any metallicity.
Thank you very much.
So there is a last question from Gayatri, please.
Hi, Isabel. I have a quick question. I was just curious to know roughly what's the alpha CO values do you get if you use like a higher carbon abundance to calibrate it, like around 7, let's say 7×10 to the 5. I think some studies have got similar values too. So just curious.
I will have to get back to you on that because I haven't tried that.
I mean, that'll be super nice to see if it goes even below 0.8 in that case. So I don't know. That'll be, yeah. Just
definitely something worth checking out.
Okay. Thanks.
Yeah.
Okay, so I would say this is the end of our morning session.